Good day everyone and welcome to our presentation. Today, representing Group D for BJTHK3053 Project Management, we are excited to present our comprehensive project plan for the DKG7 Cafeteria Construction Project in UUM. We would also like to extend our gratitude to our lecturer, Prof. Madya Dr. Muhammad Faizal bin Ahmad Zaidi for his guidance to us. Before we dive into the detail, let me introduce our team member. The individuals that driving this project forward are me, Nur Hafiza, my other friends is Nur Shahira, Amanina Akila, and Nur Ilma Dalila. Together, we have collaborated across various management roles to ensure the structural and strategic success of this project. Let's start with our framework with Part A, which is Project Scope Management. Defining the scope is the process of precisely recording and regulating exactly what is, and just as importantly, what is not included in the project. By establishing the strategic blueprint early on, we effectively prevent scope creep and resource strain, ensuring that our team goals, deliverable, deadlines, and budget remain strictly aligned throughout the timeline. To systematically manage the project, we have developed this Work Breakdown Structure or WBS. This deliverable-oriented deconstruction has break our complex project objective down into smaller, manageable, and work packages. As you can see from our diagram, the DKG7 Cafeteria project is categorized into 4 primary tiers, which is project planning, procurement, and material sourcing, construction and civil work, and finally inspection and handover to the UUM. This serves as the bedrock for our cost estimation and scheduling. Next, to guarantee flawless execution, we look at accountability via the Responsibility Assignment Metric or known as RACI chart. A RACI matrix clarifies team involvement across 4 levels, which is responsible, accountable, consulted, and informed. On this slide, we have mapped out our primary stakeholder role codes, which is PM stands for Project Manager, CE for Civil Engineer, QS for Quantity Surveyor, and GC for General Contractor. And the last one is MEP for our Mechanical, Electrical, and Plumbing Specialist. Here is the detailed mapping of our project activities from Task A to K against our stakeholder roles. For instance, the civil engineer is primary and responsible for structural blueprint and permits, while the general contractor takes the lead on responsible execution for physical tasks like site clearing, brick layering, and painting. Meanwhile, the project manager actually maintains total accountability across every single phase to guarantee a smooth structure handover to the
Next, we move to the Part B, Project Diagramming, Scheduling, and Milestone. This slide shows the Activity on Node or AON diagram for the DKG7 Cafeteria Construction Project. Each node represents one activity while the arrows indicate the dependency between activities. From this network, we identified the critical path, which is highlighted in red. The critical path is the longest sequence of dependent activities and determines the overall project duration. Any delay in these activities will delay the entire project. After developing the network diagram, we calculated the earliest start, earliest finish, latest start, latest finish, and slack for every activity. Activities with zero slack form the critical path and must be completed on time. Meanwhile, activities with positive slack have some scheduling flexibility, allowing the project manager to adjust resources without delaying the overall project. This Gantt chart presents the overall project schedule for the DKG7 Cafeteria construction. It shows the planned start time and duration of each activity from the site survey to the final handover. The chart helps the project team monitor progress, coordinate activities, and ensure that all tasks are completed according to the schedule. Based on this schedule, the total project duration is 98 weeks, which is well within the client's requirement of completing the project in less than 24 months.
Next, we will look into Part C of our project, focusing on project resource management for the Cafeteria DKG7. Our primary goal here is to establish modern planning, scheduling, and allocation technique for our construction labor. By implementing structural labor distribution and smart resource smoothing strategies, we guarantee that the cafeteria is delivered strictly on schedule without any costly delays. Over our 98-week timeline, we ensure that every task is assigned specific labor qualification. This dynamic management approach is crucial to preventing over-allocation and site overcrowding, which is ultimately enhance our workplace safety, keep costs under control, and avoid sudden disruptive layoff. Moving on to our next slide, here we have the baseline table representing our labor requirement per activity. This table serves as our operational blueprint. It lists each project task from activity A to K, detailing their individual duration, the key responsible roles required, such as project managers, civil engineers, and general contractors, and the corresponding weekly manpower demands. By looking at this baseline, our management team can clearly map out the raw unoptimized workforce footprint across the entire construction life cycle before we apply any scheduling adjustment. To optimize this workforce footprint, we utilize a resource smoothing. By applying forward and backward pass formulas, we are able to calculate the exact operational boundaries and the total slack available for each work task. Through this analysis, we divide our project schedule into two main parts. First, the critical paths, spanning activities A through K. This part has a total slack of 0, meaning there is absolutely no room for flexibility. Any delay here will directly push back the final handover date of our cafeteria. Second, we have our non-critical paths, specifically activity H, which is involved external door, window, and drainage possess a comfortable total slack of 2 weeks. This critical finding gives us a flexible window to strategically delay or shift activity H without affecting subsequent tasks or delaying our final deadline. However, when we initially schedule everything using early start dates, we identify a major resource conflict. As you can see in the baseline data, we hit a massive operational resource spike during weeks 81 and 82, where we suddenly require a peak of 8 workers daily. The direct causes of this spike is that activity I, which is handle electrical and plumbing, and activity H, handle doors and drainage, are scheduled to run concurrently. Having 8 workers on site for just a brief 2-week window is highly inefficient. It leads to site overcrowding, overallocates our specialized crew, and causes sudden unnecessary mobilization costs. We knew we had to find a smoother solution. To resolve this conflict, we implement our strategic rescheduling solution. Since activity H has 2 weeks of available slack, we shift its start date from week 81 to week 83. The result of this resource smoothing process are highly successful, as shown in the this before and after histogram. First, our peak labor demand during week 81 and 82 instantly dropped from 8 workers down to just 4 workers only, representing a reduction of 4 peak workers. Second, we achieved this optimization with absolutely 0 project delays. Our strict 98-week delivery target is maintained flawlessly. In conclusion, this smoothing process successfully flattened our hiring curve, streamlined our on-site workflow, and completely eliminate unnecessary mobilization overhead while keeping our final project timeline perfectly on track. That's all.
Hi, my name is Nur Shahira binti Rahman. My metric number is 304344. I will covering our estimate activity cost and the cumulative budget cost for the DKG7 cafeteria project. Let's move to overview of cost planning. Effective cost planning is essential. Our primary objective is to ensure the DKG7 cafeteria project is completed within the approved budget while maintaining high standard of quality and schedule. We achieve this by estimating financial requirement for every activity, which allow for efficient resources allocation and continuous monitoring of expenses throughout the entire construction period. Moving into our estimates, as shown in the table, we calculate cost based on the total labor day multiplied by the specific labor rate. Our key finding is a total projected labor cost of 892,600 ringgit. Activity E and F covering foundation and the structural work It also contributes the highest cost due to the intensive labor requirement. In the table provided, we track our cumulative costs. By accumulating these expenses over the project life cycle, we gain the clear tools for comparing planned costs against the actual progress. Our analysis showed that costs start slow during initial planning, rise significantly during the structural phases, and finally stabilize toward the end during testing and handover. This is S-curve displayed here. S-curve visualize our expenditure over the 98-week schedule. We can clearly see the progress. First, early stage A until D, gradual growth. Second, mid stage E until F, the curve steepens, reflecting high financial commitment during the structural construction. The last stage is G until K. The rate of increase slow down and we shift the finishing work. To wrap up our assignment, we have successfully integrated our findings across the three main areas. First, scheduling and critical path, using dependency mapping to establish an optimal duration. Second, resource optimization, applying smoothing technique to balance daily workforce demand and mitigate risk. Lastly, progressive budget control, using the S-curve and our primary mechanism to minimize scope creep and ensure cost-effective facility delivery. That's all from us. Thank you.